Okay, we're up to 52 people. Last time there was like 114, so let's hang out for a while longer. Is there a way to access the Zoom recordings? I'm not sure about the Zoom, but the YouTube recordings, I'm processing the videos and throwing them up on YouTube. Let me look into that. So when I make a video, I click. Here, let me share my screen so you guys can see what I'm doing. Stop share. Share screen, screen one, share. All right, so when I make a video, it automatically drops into this like Zoom section for me, but I know that my canvas looks different than yours. And so previous cloud recordings, I have this. I have these things, and I'm not sure if you all can access this from your Canvas page. I'll try to be a student. Let's see what happens. Zoom, previous meetings. Yeah, there's no evidence of recordings there, huh? Maybe I'll look into.
Did you make a link to the? You said there's a YouTube channel with all the.
Yeah, so let me make sure my volume sounds so low. Let's see what that sounds like. Okay, that's better. Yeah, so everything you need, I'm trying to make this as online as possible so that everything you need can be found on Canvas. And so like your Zoom link is here, schedule is here, and it lets you know when I assign a homework and when that homework will be due, along with, this side panel, your to-do list. Both of the books are here. They're freely available. Syllabus, and then, yeah, something on LaTeX. And so, yeah, for each big idea, and right now we're on the personal energy use big idea of the class, I'll try to put a learning progression, trying to indicate what I think you should learn by the end of the unit. And then all the lectures. And so this first lecture we had Wednesday, so this is Energy 101 Introduction. And then within a day, I'll try to process the video and post it. I don't make it fancy or anything, so there may be like 5 minutes of dead air at the start of it. But every lecture should be here. And then as a YouTube link. And then readings associated with the lecture should be underneath it. These aren't necessary, but they'll make you better. And I advise you to read them before the lecture, then the lecture will seem like kind of a review. So all the readings are here for each of these lectures. So in this unit, there's 4 lectures and then the homework down here. And it's due October 5th. The homework says only 3 points there, and that's not a mistake. I don't go through each homework line by line looking at everybody's math. I just do a cursory glance at it and see if people made a good effort and more or less have the concepts correct, and then you get 3 points. If you're really screwing up and barely do much, then you'll get 2 points. If you just kind of write your name and attempt one problem, you'll get 1 point. And if you don't turn it in, you'll get 0 points. Then I'll post the key after the homework is due, and you can evaluate your own performance after the fact. But I'm very lenient. And again, this is a one-on-one class. I want you all to just learn some useful concepts and mathematics surrounding energy and society. And I'm not here to weed anybody out or punish anybody. So as long as you put in the effort, you should get an A. All right, let's see how many people we have now. 84. That's good enough. Let's get started. Any other questions about class logistics, that sort of thing, before we get going? And again, I hang out after the lecture too to answer all these questions as well. Chat is gone. It's always gone. Thank you. Click blue hyperlink. I was wondering how to access recordings. Okay, the readings. Okay, yeah, so to access the readings, for example, this is chapter 2, the balance sheet, which basically tells you what a kilowatt hour is, and nothing happens. Oh, I guess I'll click this up here. Yeah, and this takes you to withouthotair.com, David McKay's book. And so we're on chapter 2. If you want to get to other chapters, they're all right here. If you want to see a better visual of that, you could click Without Hot Air up here. Is my font really teeny for you guys? Probably. Yeah, so here's all the chapters. And if you really want to get into the physics of how this stuff works, you can get into these technical chapters, but that's way beyond the scope of this course. All right, let's get into it. Not seeing any other questions at the moment. Okay, so today we're continuing on our exploration of personal energy use, trying to get an idea of how much energy you use as an individual, and then scaling that up to societies. All right, so we're going to talk about heat today. It's one of the prominent uses of energy that you use, and that makes sense, right? Humans got fire from Prometheus, in the before time, and now we use it for all sorts of things: keeping our house warm, keeping our house cold, keeping our refrigerators cold, cleaning our clothes, etc. Quick recap. I think there's about 3 or 4 equations I want you to know by the end of this quarter, and this is the most important one. Power equals energy over time. So power is a flow of energy over time. And this can be rearranged, right? We could swap time and power, and then it would be time equals energy over power. So the time required to provide some amount of energy depends on how quickly you're moving that energy, the power, the flow of that energy. So when you fill your car up with gasoline, you have megawatts of power because there's just so much energy density in that gasoline. It's just flowing into your gas tank super quickly. So the power rate of a gas hose is tremendously high. Whereas when I charged my little plug-in hybrid electric car outside on my driveway there, it's only getting 1.3 kilowatts. And so it takes all night to charge my car, whereas I can fill up a gas car in a minute or so. Huge, same amount of energy, more or less, but grossly different power flows. But in general, power equals energy over time. Energy equals power times time. See, we can throw this time on the other side of the equation. So time times power equals energy, or power times time equals energy. We can rearrange this equation algebraically and solve for whatever we're concerned with. How much energy will it take? How much time will it take? How much power will I need to do a certain task? If I want to run my wood stove and run it all night, well, I can damp it way down to try to slow that power flow, but I better stock it all the way full of wood so it has enough energy that it will produce a certain amount of power over the course of 8-hour night. So useful things like that. All right. So let's look at a few different units of energy and power, and this will be a good little preview of the homework. Any ideas? And you guys can write it in the chat or just shout it out. It's a BTU, power or energy. This is British thermal unit. Somebody typed energy. Yep. So it is. I'm seeing a lot of votes for energy. It is energy. So this is a BTU is the amount of energy required to heat a pound of water by 1 degree Fahrenheit. It's a very, very human-centric unit and very English-centric unit. So, but it's what we measure a lot of our heating appliances as BTUs per hour. Now, BTU per hour, is that energy or power? If BTU is energy, then BTU per hour would be, energy over time. So it's power. It's also what your natural gas bill is billed in. It's actually billed in therms, which is 100,000 BTUs. Completely stupid unit, but that's what it is. Kilowatt hour, energy or power? See, this one's so confusing and tricky because you hear that word watt, so you think power, but it's watt. Who cares about the kilo? That's just 1,000, right? That doesn't have units. It's watt multiplied by an hour, a watt hour. So that's power times energy. I mean, power times time, sorry. Watt hour is power times energy. So watt hour, power times energy. Why did I keep on stating that incorrectly? It's power times time. So if we rearrange this equation, power times time equals energy. We can throw time on this side of the equation. And then we have time times power equals energy. Power times time, or time times power. This is actually an energy unit. And so it's really confusing because you hear that word watt, so you think power, but just look at the actual units and think about it. And then you realize that it's actually energy because it's power times time. This gets confused all the time in the scientific community, and especially in the mainstream popular press. You know, I mean, even when they say like, you know, Tesla's going to build a new battery in Australia that's 120 megawatts, and people are like, that's a ton of energy. I'm like, no, well, no, it's not. It depends on how much time it goes, right? Like a lightning bolt is 40,000 watts, but it's actually not a lot of energy because it happens, you know, in a nanosecond. So the power times time is actually pretty small. All right, barrel of oil, power or energy? Seeing a lot of energy. Yeah, this one's easier to think about because it's, you know, a bucket of stuff. Like it's not flowing, it's not power, it's not moving, changing in time. You buy a barrel of oil, you put it in your garage. I don't know why you would, but it will last there and just be the same as it was a year ago, a year later. Anybody know why it's barrel, BBL? What's that stutter about? Billion? No.
Big barrel.
Big barrel. That's a good guess. It's how people talk in Texas. Because the scientist had a stutter. British, just general British English. No, so it actually stands for a blue barrel. So back in the day, we ran kerosene lamps off a different kind of oil. Anybody know what kind of oil we used to run our lamps on? Before cars.
Kerosene?
Whale oil, yeah. So whale oil, horrible process. You guys should read Into the Heart of the Sea. The movie's cheesy. Read the book. And they would go on these incredible whaling voyages, capture a whale, and process the whale by rendering it in its own fat to drive off all the water and other volatiles. And then they would be left with this oil from the whale fat and fill up black barrels. And then in 1857, when mineral oil, or petroleum, petrol means rock, was discovered in Pennsylvania, they had to distinguish between whale oil and rock oil, mineral oil, petroleum. And so they painted all those blue. Now barrels of oil are all sorts of colors: orange, white, blue, black, whatever. Nobody cares. They're colored by the company that pulled the oil out of the ground: Chevron, Phillips 66, Conoco, British Petroleum, etc. That's what that BBL is. And I like to talk about that because it shows kind of the history of societal energy use, moving on from whales for lighting to mineral oil for vehicles mainly. Megaton TNT, energy or power? So about 50-50 energy and power. It's actually a energy rating. So this is what we measure munitions yields in, bomb yields in, and we equate, you know, the bombs that we make to how many tons or megatons of TNT it would be equivalent to. And when you're getting into megaton range, there's only one weapon we're really talking about, and that's nuclear bombs. Wouldn't it be power when it's exploding? Exactly. So it actually might be power too, because the detonation takes, a second. If you want to say it takes half a second, then you'd multiply it by 2 to get the power rating. Yeah. 1.21 gigawatts. Power or energy? Power. Yeah. So this is from the first Back to the Future, which came out even before I was born. So maybe you all haven't seen it yet. Who knows? But it's a pretty good classic movie. Anyways, the amount of power required to make the time machine work is 1.2 gigawatts. And this was obviously a script reading error. It was supposed to be gigawatts, and so GIGA, and they read it gigawatts. So, this is in their defense. Like, computers were garbage back then, so we didn't have like gigabyte drives or anything like that. So they didn't know what that word was. But that's power. All right. MC squared. Energy or power? This is silly. This is Einstein's famous equation equating energy to matter. And so matter is energy that's just collapsed in space and time onto itself. Matter is pure energy. It's just static and stays and still when we're viewing it in our current moment. And you can convert it back to energy by multiplying it by the speed of light, c, twice. And so just a teeny amount of matter can turn into a tremendous amount of energy, because the speed of light is 3 times 10 to the 8 meters per second squared. So 1 kilogram of matter would yield 10 to the 16, 10 to the 17, 10 to the 17 joules of energy, which is getting at societal levels of energy use. So it's absolutely insane. Wait, so kilowatt hour was energy or power? Kilowatt hour, I'm reading the chat. Kilowatt hour is energy, because it's power times time. Kilowatt times hour, power times time equals energy. And that's why this is what powers our sun, right? The sun converts hydrogen to helium. There's a very small mass loss when 2 hydrogens become a helium, and that small mass loss creates a tremendous amount of heat and light. And that's what the sun is. BTU, that's British thermal unit. That's a measure of heat. It's a measure of energy. Yeah. On average in the winter, I use about a therm of natural gas, which is 100,000 BTUs of energy a day. Okay. MC squared, that's energy. E equals MC squared. It's the Einstein equation. It's just for fun. Don't worry about it. All right. So today's big idea is personal energy use, heating, cooling, and lighting. These are McKay chapters 7 and 9. Again, these chapters are really short and they're fun, so don't be scared. And so to motivate this lecture, I wanted to quote Amory Lovins, who's one of the pioneers of energy efficiency. He really came out with a lot of these ideas back in the 70s. He wrote a great book called Natural Capital. And he said that utility customers don't want kilowatt hours of electricity. They want energy services such as hot showers, cold beer, and lit rooms. And so he's saying that nobody wants a kilowatt hour. Nobody knows what that is. What you want is what the energy provides. And so if we can provide the same energy service, warm shower, cold beer, using less energy, that's ideal, because then there'll be less cost to societies and less harm to environments, right? And so he was a real champion of energy efficiency. I met him 2 years ago at a conference, and I was sharing some ideas with him in front of the conference room, and he just trashed me. I was talking about, when things get more efficient, sometimes you use even more energy because it gets cheaper. It's something called Jevons paradox. And he just laid into me in front of the whole crowd. And so once again, you know, don't meet your heroes, I guess, but oh well. Still a good guy, good scientist. Maybe not a good guy, good scientist. Okay, making things hot or cold takes energy. You know this, right? You heat up a can of soup or whatever, you have to put it on a flame or put it on an electric burner. So the key concept, this is equation 2 out of 4 that I want you to learn this whole quarter is heat capacity equation. So how much energy is required to heat 1 kilogram of stuff, an element, a molecule, whatever, by 1 degree Celsius. So that's the equation in words. How much energy does it take to change the temperature of something? Some things change temperature rapidly when we pump energy into it, and some things change temperature very slowly. Can you think of something that changes temperature rapidly when you heat it? Metal, exactly. So a lot of pans are just made out of metal because we can quickly transfer that heat energy from your stove into your food. And then once you get fancier, chefs want pans that are less conductive of heat so that you can keep the temperature more stable. Yeah, copper. Yeah, these are all good conductors of heat. So what's something that when we heat it up, it doesn't change temperature very rapidly? Water. Yeah, water is crazy, has a crazy high heat capacity. And that's why the temperature in Bellingham's always like 50 degrees, 50 or 60 degrees. Because we're next to this giant chunk of water. It's this huge heat sink. And so when it gets hot out, the heat goes into the water. And when it gets cold out, the heat comes out of the water and just kind of keeps Bellingham at a relatively constant temperature. I mean, compared to the same latitude, 49 degrees north or whatever, you can go to 49 degrees north in North Dakota. And in the summer, it's hot as that word. And then in winter, it's bitter cold. Like you die in the summer or the winter if you go outside in North Dakota. So water is a huge buffer for Bellingham because it's huge heat capacity. Other things, yeah, rubber, brick, air, these are all good insulators, meaning that they take a lot of energy to change their temperature. That's what your blanket is, right? At night, it's wool or cotton or polyester and a bunch of little air pockets within that wool, cotton, or polyester. And that's why you have a blanket at night, because it prevents you from really feeling the temperature out in your room, right? So your room can go down to like 60 degrees and you don't get cold because you're a blanket. Cool. So here's the equation in mathematical notation. Don't get scared. This triangle stands for delta. It means change. So a change in energy will cause a change in temperature, a delta in T. A change in energy will cause a change in temperature. And that change in temperature will be modulated, or it will depend on these two variables. M is mass, so that makes sense. If I have more stuff, then the change in temperature won't be as big for the same amount of energy. I pump energy into it, and more of that energy will just go into this M term rather than the delta T term. So the more stuff you have, the more energy you need to change its temperature. Should be obvious, right? If you're cooking a chicken nugget versus a turkey, you need a lot more energy to change its temperature. This is funky. So this is C sub P. It means heat capacity. That P just means that constant pressure. Something we have to worry about in physics, but not in societies, because we're always at 1 atmosphere, 1 bar, because we're usually on the surface of the planet. It's a good place to be. So in this class, everything will be C sub P, and we're only really looking at water because that's what we heat and cool in our homes in society. So to change something's temperature, you have to put energy into it. How much its temperature changes will depend on how much stuff you have and its heat capacity. Water has a really high heat capacity. Blankets have a high heat capacity. Metal has a really low heat capacity. Okay. The units, messy, but let's look at them because I want you to get more and more comfortable using units. So we'll still use joules because we're using standard metric units, standard international units. And so a joule of energy will be required to change the temperature of something. And we measure temperature in Kelvin. Celsius works fine too, because Celsius and Kelvin have the same step in a temperature ruler. Like 1 Kelvin equals 1 Celsius, 5 Kelvin equals 5 Celsius. The change, not absolute, right? 0 Celsius is actually 273.15 Kelvin. Don't worry about that. Point is, in this change in temperature, you have to stay in the same units, either Kelvin or Celsius. Do not put Fahrenheit here or you're going to screw up, because the heat capacity, this constant, depends on Celsius or Kelvin, not Fahrenheit. But I'm not going to be sneaky. All the problems I make, I'm just going to keep things, I think, in Celsius, so we won't have to worry about Fahrenheit. All right, so mass is in kilograms, temperature is in Kelvin, heat capacity is joules per kilogram per Kelvin. So what is this saying? It's saying if I want to change the temperature of something, it will have this heat capacity, and it will be required to change by that much heat capacity to change a kilogram by 1 degree Kelvin. And that'll tell you how many joules we need. Okay, let's look at an example. All right, so the heat capacity of water, this is the only real one you need. In that equation, could K for Kelvin be swapped for C for Celsius then? Yes. So this delta T that we're looking at, it's looking at a change in temperature. So say you want to change the degree of your room from 65 degrees to 68 degrees. This would be in Fahrenheit. So let's say 25 to 27 degrees Celsius. Then that you take that delta, which means the difference. So 27 minus 25 equals 2. God. Sorry. Language and math take the same part of your brain, so you can't do math and talk at the same time. So that delta, 27 to 25, would be 2. You could also just do that in Kelvin, right? So it'd be like 200 or it'd be like 300 Kelvin to 298 Kelvin or something like that. And so that delta, 300 minus 298, would still be 2. If you put it in Fahrenheit, you're going to screw up, because the step in the Fahrenheit ruler is different than the step in a Celsius ruler or Kelvin ruler. It's like 4/9 or 5/9 or something weird like that. All right, so let's look at a practical example, making tea. So heat capacity of water is 4,200 joules per kilogram per degree C. So that's those funky units, joule over kilogram over Celsius or Kelvin. How much energy does it take to heat the water for 12 ounces of coffee or tea? So we can run through this. It requires conversion from ounces to grams, because the heat capacity equation depends on grams or kilograms. So let's do that first. 12 fluid ounces. Yes, you have to say fluid ounces because American units are crazy. An ounce is not equal to a fluid ounce. Fluid ounce is actually a volume. 12 fluid ounces of water is 29.57 milliliters. So we're talking about volume here. And so when you make a conversion, you're trying to get rid of the unit you don't want anymore, in this case, fluid ounces, by multiplying it by some equivalency of the unit you do want. And we know that 29.57 milliliters is exactly equal to 12, or is exactly equal to 1 ounce, 1 fluid ounce. So the fluid ounces cancel, and now we have 12 times 29.57 milliliters. That's what 12 ounces is. So what, like 350 or something. Oh yeah, right here, 0.35. All right, so now we need to convert from volume in milliliters to mass. And this is why the metric system is great. 1 gram of water is 1 milliliter. It's 1 equals 1. It's wonderful. All right, so 1 gram is 1 milliliter. And then we're converting to kilograms, and kilo means 1,000. So 1 kilogram equals 1,000 grams. And so after running through this multiplication, this conversion from fluid ounces to milliliters, milliliters to grams, grams to kilograms, we're left with the mass of 12 ounces of tea is 0.35 kilograms. All right, so we figured out one of the parts of the equation. We need mass, heat capacity, and change in temperature. Oh, I guess we have heat capacity right here. So now we just have to think about the change in temperature to determine how much energy we need to make tea. All right, so yeah, we got mass is 0.35, heat capacity as 4,200 joules per kilogram per degree C. Now we just need delta T. All right, so delta T, what's the boiling point of water in Celsius? Any thoughts? Yeah, 100. I'm seeing a few people write 100. So again, this is why metric system's convenient. Boiling point of water in the metric system is 100 Celsius. Should we memorize unit transfers? Absolutely not. Yeah, the test will be open notes, open book, open internet, not open to collaboration though, right? Don't go to chegg.com or whatever. Don't be a jerk, and don't ask your uncle or aunt who's a chemist for help or something like that. It's for you to work on alone. Homework, collaboration, go for it. But the tests, open everything, but don't cheat. You know what cheating is, right? You know in your heart. I don't memorize these. I don't memorize these unit conversions. I'm starting to, just because I've said them so many times, but yeah. Okay, so to boil water, you need to get up to 100 C. Room temperature is 20, 25 C. And so the delta is therefore 100 minus 20. The change in temperature is 100 minus 20 is 80 degrees. We're heating this water by 80 degrees. So again, the amount of energy that is needed to heat the water depends on how much water we have, the heat capacity of water, and how hot we want to make it. We want to make it twice as hot, it's going to take twice as much energy. We have twice as much water, it's going to take twice as much energy. Okay, so we have all the pieces now. Let's run through the math. So delta E equals mass times heat capacity times delta T. Mass is 0.35 kilograms. Heat capacity is 4,200 joules per kilogram per Celsius. This to the -1 just means it's on the denominator. It means it's below that line. That's what the -1 means. Sorry, I should not use as much scientific notation, but that's what that means. So joules per kilogram per degree Celsius. And then the delta T, again, is 80 degrees C. So cranking through that math, we get 117,600 joules. Lifting an apple from a desk 117,000 times. It's the amount of energy required to boil water for tea, 12 ounces. If we converted that into a kilowatt hour, we call from Monday's lecture when we solved what a kilowatt hour is, it's 1,000 joules per second, that's what a watt is, multiplied by the amount of seconds in an hour, which is 60 minutes per hour, 60 seconds per minute. 60 times 60 is 3,600. 3,600 times 1,000 is 3.6 million. So that's where this unit conversion came from. So we're trying to get rid of joules here to see how many kilowatt hours this is. 1 kilowatt hour of energy is 3.6 million joules of energy. So 117,600 divided by 3.6 million equals 0.032 kilowatt hours. Not a lot, right? Remember, a kilowatt hour is like 10 cents. Wait, why is kilogram in C to the power of -1? This is shorthand notation for putting something in the denominator. Can I write on stuff? Does this work? I'll try this. So like, this means 4,200. Does my pen work? Yeah, this will be joules per kilogram Celsius. So that's what that means. Like, if I had 2 squared, that equals 4. If I had 2 to the -2, that equals 1 over 2 squared equals 1 over 4. Savvy? All right. Hang out after class if you need more help with that. Okay, stop. Oh, bother. Clear all drawings. Okay, so the heat capacity of water, okay. How much energy does it take to heat the water for 12 fluid ounces? It takes 117,600 joules or 0.032 kilowatt hours. Does this make sense? I guess. Let's test it, right? This is what science is, right? You observe nature, you formulate a natural law that describes that behavior, in this case, delta E. The amount of energy required to change the temperature of something depends on what it is, that's heat capacity, and how much of the stuff you have. Kilowatt hour is energy. It's power times time. It's super confusing. You have to just hammer it home for a while. Read McKay chapter 2, and it'll start to make more sense. Okay, so let's test this out. Let's see if this actually is true or not. Before we do that, let's guess how much time it'll take. So how long will a 1.5 kilowatt kettle be on? So the amount of power that comes out of a wall in America is 1.5 kilowatts. And most kettles are going to be a little less than that because they're not perfectly efficient. They don't perfectly turn that power into, or they don't want to ramp right up to 1.5 and blow a fuse. So when we do the question, does it matter if we end up with joules or kilowatt hours? No, it doesn't matter. They're both measures of energy. If you converted it to like barrels of oil, I might be pissed off because that's ridiculous. But like as long as they're sensible units of energy, that's great. So how long will this take? Let's look at that for a sec. Stop share. Share screen. Let's grab this this Photoshop thing. Can you guys see that okay? All right, I'm gonna try this again. Hopefully it's not as painful as last time. All right, so how long will it take? So I'm trying to think about time here. We know that power equals energy over time. So therefore, time equals energy over power. So power is on the denominator. That means as this number gets bigger, this number will get smaller because we're dividing by a bigger and bigger number. So the more power we have, the less time it will take to provide a certain amount of energy. That makes sense, right? Because you're just pumping that energy in. So the amount of energy was 117,600 joules. And the power is 1.4 kilowatts. This equals 117,600 joules over 1,400 joules per second. Because that's what a watt is, right? A watt is a joule per second, and a kilowatt is 1,000 joules per second. So multiplying that 1.4 by 1,000, you move the 1.4 times 1,000, you move this decimal point over, you get 1,400. All right, so then this is going to equal, we can kill these zeros, these joules cancel. 1 over seconds equals seconds. This 1 over 1, it's over it twice. And so we're left with seconds. Time equals seconds, so that's good. because time should be in seconds. It should be in some unit of time, hours, days, years, seconds, millennia, whatever. And so now we're left with 1,176 divided by 14. That's about like 1,200 divided by 14, which is kind of like 1,400 divided by 14. So that equals 100, but I got a couple extra 14s here because I went from let's see, what did I do here? I need some extra because I have about 200 extra here, 300 extra here. So let's call it like, I don't know. Maybe I should just do the math instead of doing it super fast like this. Phone. One 176 divided by 14 equals 84. I was going to say I have a couple extra 14, so let's take 20 away and make it 80, but that was kind of close. So let's say the answer is 84 seconds. Sorry how messy this is. I'm not used to these electronic pads. Okay. So time equals 117. I'm going to make it clean. 14 watts joules equals 84 seconds. And 84 seconds equals 1 minute and 24 seconds, right? 60 seconds in a minute. Right, chat is doing stuff. Let's see what's happened. Okay, oh, people are helping me out. Thank you. Okay, so let's go back to the PowerPoint. Share screen. Let's do all of screen one so you guys can still see this math. So how long does this take? We guessed 1 minute, 24 seconds, or we calculated, we didn't guess, we were scientists. We calculated 1 minute, 24 seconds, and we think it's gonna take 0.032 kilowatt hours. So 84 seconds, 0.032 kilowatt hours. Let's see if that's true or not. So. I have some tea water. I'll stop sharing my screen so that you guys can see me. I got some water here. I'm gonna make some tea. Here's a tea kettle. Gotta do 12 ounces. 12 ounces was 0.35 kilograms, right? So that's 350 grams. Here's a tea kettle. Let's switch cameras for you. Video, this one. Okay, let's focus. All right. Tear. Don't be making guesses about my habits just because I have a very sophisticated scale. It's for espresso. Okay, let's tear that again. All right, so we need 350. 357. 350.5, that's good enough for me. 351. All right, so a teeny bit more. Let's ignore that. Okay, so we say it's going to take 84 seconds and 0.032 kilowatt hours. This thing here is rad. You should get it and annoy your roommates. It's called a kilowatt. I think they're like $30. We do have like 100 of them in the tool lending library at the Institute for Energy Studies, but I don't think that's open because of coronavirus. But when that gets over, you can borrow it. You can check it out from me. Just ask me if you want it. All right. So right now it's saying that there's 121.4 volts coming out of my wall. That makes sense because America has 240 or 120 volts. And then you can switch to watts. Right now there's 0 watts coming out of this plug. That makes sense because nothing's plugged in. All right. So let's plug something in. Here's the kettle. Plug it in. It's still at 0 watts. Why? So I didn't
You haven't turned it on yet.
Yeah, it's not drawing any power. So as soon as I turn on, it's going to start drawing power. US outlets are rated for 1500 watts, 1.5 kilowatts. It's probably going to pull less than that because you don't want to blow a fuse. Plugs in England are actually rated at 3000 watts. And so it takes half as long for them to make tea. And it's because they take tea seriously, you know? Okay. So let's see how long this is going to take, how much energy it's going to take. Stopwatch, reset. All right. So when I turn it on, it should get up to a certain amount of watts. And then I can switch and press this button and see how many kilowatt hours of energy I'm consuming. All right, so but let's get on watts first just so we can see how much power gets drawn. All right, this won't be exactly in sync, but okay, started the clock. So it's pulling 1,370 watts. That's pretty standard. So not quite 1,400. Taking some time. It's like ASMR or whatever. Yep. This is what we're doing. We're boiling water in class. Thought I'd watch Pot Never Boils. I mean, you guys are paying good money. That's why I'm providing you with this education, right? You know, making tea. Okay, let's switch over to kilowatt hours, see how much. So far we've burned 0.01 kilowatt hours. Got a minute. Oh no, the kettle turned off? We still drawing watts? We are not drawing watts. Quick, I'll be right back. I'll be right back.
We miss you.
I take coffee very seriously, so I have a backup kettle. This is actually the one I usually use, but I wanted to use that other one because it's sucks. No, I wanted to use it because it doesn't have any insulation. It leaks heat. This one's better. All right, so let's do this again. Start. All right, so this kettle actually is pulling 1,400 watts. going. Come on. See how many kilowatt hours we're up to. 0.2. Point three. Point four. Starting to see a lot of steam. We're past 84 seconds. We're now at 94 seconds. Changing pitch. Sounds very boily right now. And it's boiling. Okay. Phew, how exciting. Okay. So it took 30 seconds longer than it should have. And it took about 0.202 kilowatt hours more than it should have. What happened? Why is physics a lie? Any thoughts? Oh, I see. Sounds very boily. It does. So we evolved to hear hot water, right? Hot water is less dense, and our hearing is really well attuned to that difference in water density. And that's why we don't accidentally fall into, a boiling hot spring or something like that. Entropy, because real life isn't perfect. Real life isn't perfect because of entropy. So what's happening, that not all the energy from the plug is going into heating the water. Some of that energy is going into other things. For example, the sound of the water moving around. It's mainly going into waste heat. What's waste heat? It's heat that's going everywhere around the room in the atmosphere. So this kettle, if I touch this lid, it's super hot. This is not what I wanted to heat up. I wanted to heat up water, not this lid. If I touch the metal rim right here, I would burn myself. And so all this energy is going everywhere. You see the steam coming out of it. So energy is being lost all over the place and radiating around the room, heating up the entire room by some teeny amount. Wire resistance, yeah, some of the energy is lost in the wire itself. I had the kilowatt, all sorts of different contraptions that have some teeny loss of energy there. And so it would have been much more disconcerting if we got an answer that was less energy and less time, because that means we violated the first law of thermodynamics, which is energy is conserved. Energy equals energy. Second law of thermodynamics says that when you change forms of energy, when you go from electricity to heat, for example, it's not perfect. Some of it's going to get turned into waste, turned into entropy. And that's what happened here. And that's why it wasn't perfect. It's too late in the day for espresso, so I'm not going to have an Americano, but I don't like wasting energy. So I'll have jasmine green tea. That'll be nice. I got 2 beverages, Topo Chico and green tea. I'm set for the rest of the lecture. Okay. All right. Questions about that? Let's see. Okay.
I have a question about.
Go for it.
The outlet, what are they called? That thing that you plug your kettle into, the thing with a bunch of plugins?
Oh, power strip?
That power strip. Does that draw more energy from the outlet?
No. I mean, no. it's no different than basically the wires inside your wall. So the wires inside your wall is the string of wires, and each time there's an outlet, the outlet connects to those two wires and makes an outlet, usually twice. That's why there's two plugs in each outlet. And then that string of wires continues down. And what the power strip does is basically just continue those two strings of wire. It's called parallel, and allows more outlets.
It just extends.
One problem that it has is if you overload your power strip, then you're gonna demand far more than the 1500 watts that comes out of your wall, and then you'll blow a fuse. And the power strip ideally prevents that. The power strip will trip, it'll break the circuit before you blow a fuse. And it works the other way too. If there's too much current coming into the power strip from a lightning bolt or something, then it'll trip and save your computer.
Thank you.
Yeah. All right, so what happened? It took more energy, it took more time than we thought, because not all of that energy was perfectly converted into hot water. Some was converted into heating up the kettle itself. That's probably the main sink. The other principal sink was heating up the room around the kettle. And then the third sink would be sound and motion and that sort of stuff. Motion of air currents, and sound, which is motion of air currents, pressure waves going through air. How much would this cost? Half a cent. So that $2 coffee you get at Starbucks, you're paying for the coffee beans, right? And someone to smile at you, not for the actual energy required to heat it up. Okay. Oh my God, it's way over budget. Somebody said have to go to work. Bye y'all. I'm sorry about that. It's the tea kettle thing. All right, so the rest of this lecture, we look at, I'll just do like 3 more minutes. Is that okay? If you have to leave, I totally understand. You can see everything from McKay's book and from this lecture. Okay, so space heaters, they draw 750 to 1500 watts. Why? The max they can draw is 1500 watts, and they usually have a medium and a high setting. The medium, they just cut it in half. It's nothing fancy. How much energy will this consume a day? Well, if it's at 1000 watts, then energy equals power times time. So 1 kilowatt, 1000 times 24 hours would be 24 kilowatt hours, or 24,000 watt hours. That's how much energy it consume. I'll talk about this next time. Should we heat with natural gas or electricity? Depends. What's the source of your electricity, right? Dishes and clothes. Washing machines and dryers, they have the fancier outlet in America. They're like more triangular shaped one. And so they actually can pull 2.5 kilowatts instead of 15. The amount of energy you use for washing clothes per day is about 3 kilowatt hours total for the washing and the drying. Notice the drying is much more, or it's twice as much as the washing. That's because of the heat capacity of water, right? You have to heat that water up and drive it off. You have to evaporate it. That takes a lot of energy. So save some energy, do it inside your house. Well, it still takes some energy because that energy came from somewhere. It came from your house. By drying clothes inside your house on a clothesline, you're cooling down your house. And it'll take about 0.5 kilowatt hours of more heat in your house. Line drying outside, that's for free. Mother Nature does it for you, but it's a hard thing to do here in Bellingham. Right. Dishwasher, about 1.5 kilowatt hours per day. Again, that's all has to do with heating water. This is all heating water. That's what this energy is. Keeping it cool. This can be quite energy intensive. Typical ACs consume about 7 kilowatt hours per day when on, not because of the heat capacity of air. The heat capacity of air is pretty low, but you just have so much air in your house that you have to change the temperature of, and you have to change the temperature of your walls and your floors and ceilings and stuff like that, because that's touching the air. AC use is much higher in a place like Houston, Texas than it is in Milan, Italy, even though they're at the exact same latitude. Why is this the case? It's because of what the stuff is made out of. Remember, part of that heat capacity equation is not only mass, but it's also the heat capacity of the stuff. So this is made out of metals, which change temperature more rapidly, and glass. This is made out of marble and stone, right? So huge amount of mass of stuff with a high heat capacity. And so it doesn't change temperature too much. And that's why it's cool when you go into like an old stone building, right? Yeah. The more thermal mass you have, the more heat capacity you have, the more stuff you have, then you don't need as much energy to change temperature. Temperature won't change as much with the same energy input, namely from the sun. It's also why we keep wine in the ground, because the ground is a big heat capacity sink, and so the temperature of your wine won't change and won't make bad wine. It's also why we put bodies 6 feet under the ground, because we don't want temperatures changing and causing things to off gas. Try not to be too morbid. Lighting, we'll talk about next time. So in summary, hot water for cleaning and cooking is about 12 kilowatt hours per day per person. Heating homes and buildings, it's bigger because they're bigger, more mass, 24 kilowatt hours per day per person. And then cooling for food in your refrigerator, about 1 kilowatt hour per day. Lighting for home and school, about 4 kilowatt hours per day, probably less with LEDs now. All right, questions, thoughts, concerns? See the chat. All right. When are we going to start working on the homework together as a class? That will, where's my internet there? Sometime next week. The schedule is on Canvas, and I mentioned whenever we work together on that schedule, so let me pull that up for you. So it's here. Can I zoom in on this? Yeah, so the first homework is due, so homework in October 5th, and live recorded study session will be Friday the 2nd. So I'll post that on YouTube Friday night or Saturday morning, and then you'll have the weekend to review that and get the homework turned in before lecture on Monday at 1:59 p.m. And we'll all work on it together. And we'll do that for every single homework. You can see this, live study sessions, study sesh, got lazy, I guess. Yeah, it's all there. Don't know if I have one for this one. Maybe I'll do it here, free day recording for the podcast. Okay, let's get back to the chat. Let's do it. I'll probably say, all right, cool, true. I'm gonna tell my mom about making T energy. Can you give us a couple example of power units? Horsepower. So that's the equivalent power that a horse can exert when it's pulling a plow. It's equal to about 7 people. People is 100 watts. It's crazy how little power we are. It only takes 100 watts to run a human. And I think it's a testament to how amazing our brains are, how efficient our brains are as a computer. Other units of power. I mean, power is energy over time. So BTUs per hour is one that I frequently see. Kilowatt hours per day. That's something I see a lot. Yeah. Other questions. What makes something a better or worse conductor? Oh God, this is quantum mechanics. It depends on valence electrons and the structure of the atoms. So things that are more metallic can conduct heat and electricity much more efficiently than things that aren't metallic. Got a little lost in the math, probably because of the quick unit conversions. Are there any resources for us to practice this kind of problem? The book, McKay's book, it would be your best resource. He really diligently goes through these unit conversions. Talking with me outside of class right now could also be useful. Yeah. Maybe just Googling around unit conversions. I would recommend you go to the Math Study Center, but I don't think that's open because of coronavirus.
Oh, the tutoring center is still open. You can make individual meetings online with them.
Oh, awesome. Thank you for that.
Totally.
Yeah, unit conversions, you basically just want to get rid of the unit that you don't want and replace it with the one you want with some sort of equivalence. So I can run through a quick example of that. New share, let's get Photoshop back up. Get a new layer, get rid of that first layer. So, one that you're probably familiar with is, 1 pound to 2 kilograms. So that's something you might see pretty often. And so the equivalence is 1 kilogram equals 2.2 pounds. And so to solve this equation, you take your 1 pound, and multiply it by something that's equivalent, meaning that it equals 1, that cancels the unit you don't want anymore. So we know that from this, we could put 2.2 pounds on the bottom because we're trying to kill that pound, and that kills it. And then you put the equivalent of 1.2 pounds up here in the unit you actually want, which is kilograms. And so then we see that 1 pound equals about 0.5 kilograms. It's Friday. We can talk about beer. So how many cups equals a pint, right? That's something that you probably know from cooking, that 1 pint equals 2 cups. And so if you have 2 pints of beer, how many cups? Well, you'd have 2 pints. That's what we know. Trying to multiply it by an equivalence. An equivalence is something that means the same, but it has different units. You put the unit you're trying to kill on the bottom, so that's 1 pint or a pint, and you put the unit you're trying to get on the top, and we know this equivalence is 2 cups. So 2 pints equals 2 times 2 equals 4 cups. Starting to make a little more sense. Our homework needs to be typed, correct? Yeah, this is university, so we got to be professionals. No more red crayon allowed. Unless you have if you have a disability that prevents you from using a keyboard or quickly, then I'll certainly accept handwritten or other forms of submission. Blue crayon, nope. We'll get through it. Again, we'll have the study session next Friday. And again, this is as hard as the math gets. I just wanted to start out with all the mathiness that would be entailed in this class so that people know what they're in for and, have an opportunity to drop if they want to. But I would just encourage that just because we can get through the math together, and there's other aspects of the class that aren't reliant on math. All right. No, the study session, is October 2nd. That's Friday. And then it's due October 5th, which is Monday. So you got a weekend. What is the actual objective of the homework? To practice using some of these concepts, namely power equals energy over time. Learning, I think. I don't know. I don't know what the point of anything is, to be honest, but I've tried to make the homework be, what problems do we use? I mean, the problems that are on the Canvas page. So you'll use the power equals energy over time equation. So if I click the homework, sorry, I need to get a new share going. So I click the homework on Canvas. I'll do that again. So idea 1, homework, personal energy use, PDF, assignment 1. We open that up. Now I gotta get a new, okay, luckily it stayed in here. Oh God, come on Zoom. Here it is. It's probably poor resolution. I can zoom in. So it talks to you about how to turn it in, what sort of equation editors you can use to do the homework. Microsoft Word has a decent one. Google has a better one. The best is LaTeX, but it's super nerdy. Don't do it unless you like that sort of thing or want to get into like computer science or STEM fields. I made the homework in LaTeX. It makes pretty equations. There's an example question and an example answer that you don't have to do, but it shows you, some unit conversions and the techniques for completing the homework, in an exemplary fashion. And then there's this first problem. You have to think about these different energy or power units and say whether they're power or energy. So it'll take you, some thinking about what these units actually mean. Something like calories. Well, that's what a candy bar is rated as. So that's probably energy because it's something you can hold. It's not like changing in time or moving. Greek prefixes. So you got to get used to things like kilo and mega. Stuff you can look up on Wikipedia or all over the place. Chat is doing something else. Have a good weekend. Good to see you. I'm gonna go shower. That takes about 2 kilowatt hours. Yeah, so here's showers versus bath. This will be the hardest problem, and this is what we'll probably work together on October 2nd. So we have to think about water flowing out of a shower. And when you think about that, that's a flow of water, but it's hot water, so it's actually a flow of energy too, right? There's energy coming out of that shower head. And so we have to think about how much energy it is by thinking about how long the shower is going. Power equals energy over time. So rearranging that equation to think about power and time and energy for taking a shower, and then comparing that to a bath. The whole answer is in McKay chapter 7. You can check it out. And then a little bit about your energy burn rate, your power rate. So what does it mean to be a human being? How much power is flowing through you at any given moment? We can figure that out by thinking about how much food we eat over the course of a day and back solve it for that. And again, it's small. It's like 100 watts. You said you'd record the study Zooms too? Yeah, definitely. All right. Got 25 people left. Anything else? Are you guys just hanging out to see what other questions get proposed or answered?
Professor, I got a question.
Yeah.
So you said we can use something from like Microsoft to turn the assignment in?
Yeah, just Microsoft Word has an okay equation editor.
Well, I was gonna say I use like OneNote and everything to just take the notes for the class. And
Yeah.
it has a full equation thing. Like I can just post it in the chat real quick, like what we were doing earlier.
Okay. Yeah, then great. Yeah, whatever you can use that ultimately you can print or save as a PDF. And I know you can print as PDF from OneNote. Yeah, that looks great.
Okay, so cool.
Yeah, that looks great. And so then, yeah, print it as a PDF or save it as a PDF if it's allowed, and then submit that. And I say PDF just because Canvas sometimes has trouble with different file formats, and it has no trouble at all with PDF. But that's all mentioned in the homework. Yeah.
Okay, cool. Thanks.
All right.
I have a question about the McKay readings.
Yes.
So in the schedule, it says this was for last class. The readings were 1, 2, 3, and 5, but on Canvas, it only has the readings chapters 1 and 2. I was wondering if you just recommend reading chapters 3 and 5, or if that's not necessary, or what?
I have no idea what I was thinking. 3 and 5. Oh, just because I talked about cars a teeny bit, if you wanted to really think about how much energy a car takes, that's where I pulled those lecture slides from.
Okay.
Yeah, and I should have linked them on Canvas too. I didn't. My bad.
Okay. That's all I need to know. Thank you.
Yep. Good question. All right. It's going to be hard to remember people's names in these online classes, but I'll start to remember some faces at least. So thanks for hanging out. Have a good weekend, and I'll try to check the email every once in a while. Bye.